we play our cards right on this one, no pun intended about playing cards. If we play our cards right with this one, we should be able to knock this out between today and a little bit of tomorrow. And then that'll get us Friday, like the last half of tomorrow, and then into Friday to work with normal distribution stuff. Which means we'll be able to review everything Monday, test out Tuesday. And it actually winds up with a little bit more review than I had thought of. Which is great, which is fine, which is super.
Wait, because it has to be on Tuesday?
Yeah, I think so. I think we'll be okay with that. I don't see it being a big deal. 12-7 is one of the cooler things that we can do. As cool as things can be in math, but it's based upon what we learned in 12-6. So we just kind of play it by ear. But we might be able to be done by then. I think that works. So let's look at binomial distributions. Let's do this. Binomial distribution. What does the prefix for binomial bi stand for from the Greeks? Two. Which basically means we're looking at stuff that has you're going to work with, it's going to happen or it's not going to happen. So the probability of an event occurring is going to be, let's say, 20%. The probability of an event not occurring would be then 80%. If you have 20% occurrence, 80% would be non-occurrence. We're going to work with that. We're going to work with some pretty straightforward stuff, but I also have figured out a way that to shorten just about everything we do in this section by using a few buttons on our calculator. But we have to understand what it's actually doing to make it work. So let's take a look at what the way that I've always started this unit is kind of just talking about, well, first of all, you've done binomial stuff. Bless you. Remember we did Pascal's triangle for that?
Yeah.
Binomial expansion? This is an offshoot of that. When we're looking at binomial distribution stuff, we're going to be using bits and pieces of the formula of Pascal's triangle of the how things expanded out by the choose, n choose r, that kind of stuff. We're going to be looking at that, but not so much in great detail anymore. Bless you.
Thank you.
Because there's a button that'll do most of the work for us. So it's not so much the idea that we have to memorize these long-winded formulas. We just have to know the correct format to put in our calculators, which is nice. So the calculator won't do the binomial expansion for you. I know, right? Be nice, wouldn't it? But at least we'll do some of this distribution stuff. So what I don't write any of this down. I want you guys to kind of read through this with me about how this works. Probability experiments, what we're looking at, there are going to be, for this binomial experiment, there's going to be an n number of independent trials. It's just going to happen. Each trial has two possible outcomes: success, failure. Pretty easy. It's kind of like flipping a coin. Heads or tails. Rolling a die. You're going to roll a 3 or you're not going to roll a 3. Success, failure. Probability of success is the same for each individual trial. If I'm rolling a die, every time I roll a die, the probability of getting a 3 is going to be what? 1 out of 6. Each and every time, it's an independent roll. It is not dependent if I roll a 3 before it, I'm going to roll a 3 again. It's not, we're not looking at things being the term loaded. You ever heard that before?
Yeah.
A loaded die means it might be weighted at some point. Might means, in other words, you're cheating. The whole nothing up my sleeves thing. You know that one? You got that one. So the idea here is that we're going to be working with some very basic probabilities to see how we can figure out success rates. Let me rephrase this. If I want to take, go back to the example of rolling a die. If I roll a die 20 times, what's the probability I'm going to get exactly 4 3s? What's the probability I'm going to get exactly 2 3s? What's the probability I'm not going to get a 3? Things like that. That's the kind of stuff that we can do with a binomial expansion. You might have done this before when you've done just a histogram chart of just some very simple tables of flipping a coin. You ever done that before? You just flip a coin and count whether you get heads or tails so many times? It's the same basic idea. but we're going to use these formulas to do it. So don't overthink this. The way I want to start this is asking you guys a very simple experimental question. This is very, very in-depth and very involved. It is, I hope that none of you get freaked out by it. You're going to be okay. But
Wait, this doesn't make sense.
the two E's.
That's like
Or maybe I was thinking about Peking duck.
Okay.
Wait, but
I don't know
if you
if
have
it
to
makes
give
sense
your
at all.
answer, yes or no, is it like raising our hand or are we saying?
Yes.
Capital letter.
Nah. Nope. Keep it.
Is that better? So, put your heads down to cover your eyes. I don't want anybody peeking. No running up and down a mountain.
I might fall asleep.
Yeah. Guarantee it's no. No, he just. Is everybody's head down?
Yeah.
No, he's outside. I'm not coming up.
Somebody was peeking. That was funny. I had to do it. Anyway, so put your heads down. I really do have a question. All right, this is legit. Now I'm not messing around anymore. I'm not leaving.
Play the game right.
I didn't,
Everybody's thumbs up.
I thought it was like.
I didn't ask the question yet. Don't put a thumb up. Jeez. So the question I'm going to ask you is whether or not you believe that UFOs exist. Don't laugh. So, if you believe that UFOs might exist, or that they do exist, raise your hand. Okay, you can put them down. If you believe they do not exist, raise your other hand. Well, you know. Okay, so let's see if anybody cheated. Did somebody not vote? 1, 2, 3, 4, 5, 6. That would be 2. Did 2 people not vote? Let's try this one more time.
Oh my god.
I know, apparently I can't count. Believe, yes or no? Raise your hand. Yes! We try this again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So I figured out who I skipped. All right, you can sit up and readjust your lives.
We open our eyes.
Yes, you may. So, out of the 29 people we have in here, we believe in the little green men, apparently. So, 15 of us in our experiment, 15 out of the 29 say yes. There are little flying saucers.
That was like a sombrero.
Yes.
There are little flying saucers flying around with little green men.
Yellow.
That's yellow.
Yeah, whatever.
I didn't even think anything.
You can't say green, you're on in yellow.
What's that?
Did you put your vote in this?
I did not, because I'm the independent arbitrator.
Whoa.
I don't want to influence you because you may influence 12th hour, and I don't want to influence other people.
I understand.
You don't say.
And then we had 14 out of 29 with a no. So what this tells us is that we could figure out the probability that somebody, that we pick one person at random in this classroom, that they believe in UFOs exist would be 15 out of 29. What's that decimal?
A number.
.517?
Yeah.
So we say 5.2, we call it a day?
Sure.
So we'll just say 0.52%. So our success rate would be 0.52. Our failure rate would be 1 minus that. In other words, its complement, convenient how that works, would have been 0.48. All right. Now, what happens here is that I wanted to look at the idea that when you're looking at binomial distributions, it's a yes or no question. I want to this is where you start to do selections of, you're going to see the words exactly, or at most, at least. You'll see stuff like that. When we read these things, you're going to randomly, all right, the way that you're going to be able to identify that it's not just a, what's the probability of picking 3 people in a row that believe UFOs, if 52% of people believe. That would have been independent, pick 3 people, just go boom, 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 multiply them together, there's your probability. What this is that you're going to specifically have n amount of trials with X amount of success. There's going to be a trial versus success for a binomial distribution. So what I'm going to say is, what is the probability that we get at least out, let's do it this way. We'll have 6 trials. I'm going to randomly select 6 people, and I want exactly, we're going to call this a k-value of 2 successes. With a p-value, this is our percent of success that we're looking at, was 0.52. We're using the data that we have in this classroom. Well, we have a very long-winded formula for this. Binomial distribution, n, choose k. I'm gonna write this all down. P to the k, 1 minus p to the n minus k. Convenient, isn't it? Yes. That's where we have, that's where the n, k's, and p's are coming from here. The n is always going to be the number of trials. K is your picks, if I guess you want to call it. How many you're picking?
Wait, what do you mean how many we're picking? Rather than like how many?
Let's say you want exactly 3 people out of 6, or you want 5 people out of 6 that you're trying. The amount you're looking for, yeah. The amount you're picking out of that, the 6 random trials, I want exactly 2 values to occur. These are the number of successes I want out of the trials that I'm picking. So out of this classroom, I'm going to randomly select 6 people. I want 2 of them to believe in UFOs.
Okay, I got it.
That's what I want.
Try it.
Does that make sense?
Yeah, I got it.
Try it.
Try it.
Well, hold on. And then P is obviously going to be our percentage of our success rate. So what you could do is throw all these values in your calculator as a 6C2, 0.52 to the 6, squared, to the 1 minus 0.52. Move this over a bit. To the n minus k, to the 6 minus 2. You can type it in exactly like that with parentheses, your choose values, and all that kind of stuff. Or, there's a little bit of a shortcut. Let me show you how this works. Let's do it this way first. If we do it this way, we have our, what was it? I forgot where it was.
What are you trying to do?
It was math? No.
It was alpha window.
It was math. So it's, if I just have to make it a 6
minus 2.
Yep, 6 choose 2, move it over, 0.52, in this case it's squared, parentheses 1 minus 0.52 to the, I could probably figure out what 6 minus 2 is in my head.
Help? Okay, back to ours.
So the probability of randomly selecting two people out of, or sorry, let me rephrase that. The probability of getting exactly two people out of 6 randomly chosen to believe in UFOs would be basically 22% in this group. That's what this stuff does. Now, the shortcut way of typing all of this in is really, really cool. What we're looking at here is a binomial distribution. In your calculator, I believe it's under, hit second bars,
Where's the
right next to the clear button.
bars? I think it's bars.
Bars. Second bars. There is an option where it says binomial PDF, and there's a binomial CDF.
Oh, it just looks like normal.
It's just normal.
Oh, scroll down. There'll be a binomial.
Oh, yeah.
Okay.
There is.
If we hit up, there's bino CDF, bino PDF.
Which one?
Well, I'm glad you asked.
We want CDF.
No, we talked about
Or what?
How do we label? We call it number of success. The Bino PDF is that you're, think of it as you're picking one specific amount of success. Pick, P, we're picking 2 successes. The CDF is going to stand for a culmination of successes. You're adding up a bunch of them, up to 3. What is the probability I'm going to get? At least 3 successes out of 6 trials. Bless you, at most 3 successes. That's when you're going to use CDF.
So PDF is exact, CDF is.
Is like a you're combining a bunch of them. You're summing them together. Okay. So our PDF is for picking a specific number of success. The CDF is when you're going to have like at least, at most, and I'll show you that example here next. Correct. So the way that you would do this is that the calculator, when you put in Bino PDF,
6.
it opens up a parentheses. The first thing you put in is your number of trials.
What's the X value?
Getting there. The number of trials, and then comma. You know where the comma button is?
Yeah, underneath. Above 7.
Whoa. Oh, did this change this? Oh.
No, you just press
Oh. Whew. Okay. Number of trials. Oh, this is different than the old operating system. Did anybody's calculators open up to a parentheses right away?
No.
Okay, I'm gonna have to do this 2 different ways then. If your calculator opened up parentheses, you're gonna have the number of trials, and then you're gonna have your p-value, comma, and then it's your k-value. Your k-value is, remember, your number of successes. N for trials, K for success, P is your percentage. So it's gonna go N, P, and K, close the parentheses, and it should spit out the right answer. Should.
Yes.
It does?
Yes.
Okay. For the other one, I didn't realize that it did that.
It gives the trials.
So if we look at that one, trials in this case should be 6. Our p-value was,
0.52.
what was it?
0.52.
Thank you. Our x value, how many we want? That's our k value if you want. We want 2. Paste. I don't know. Hit enter.
And then, yeah.
Hey, there it goes. And it does it automatically. It's going to put it in that same sequence for us. And then just hit enter.
Nice.
Hey, look at that.
It worked.
I'm not exactly sure what the paste button stands for.
Where's the comma?
Comma is directly below the sign, between 7 and sign.
Above the 7.
It looks like a period.
Does that look like a weird view?
Okay, on the calculator, like the button, it looks like a period, but it shows.
What period?
So PDF is going to be for a specific number that you want to work with. The CDFs are going to be a little bit different. Okay, the CDF is going to be a little bit different. Not too bad though.
Not at all.
So let's go here.
Yeah. Yeah.
Oh, you can actually like, test it?
Not right now. I'm not doing this with calculus, this whole thing. This is boring. So let's look at the example of up to. Gotta paste this one here. I'm going to use the book example because it's really clean. But I had it on here.
What you
I don't.
What is it?
So right out of the book, I'm going to look at. Let's go back to our UFO problem. And if we use the example they did in the book, that way you can go back and refer to it. Their success rate was 37%. So you guys are a little bit more tinfoily, I guess, than they are. So what they did here with their stuff is that they had the number of trials was 6. They want the K value was 2, and their P value was 0.37. I'm just referring back to this one for right now so that way you can go back and forth from the book how it's working. So if I redo this and I want to figure out that when we get to the idea of at least, at most, I'll show you how this works. The old-fashioned way of doing this was to go through and create a histogram. And then just count up your probabilities for the table in it. That's a pain. Calculator makes the histograms and does all that work for you, but it's still a bit of a pain. What happens is that if you're looking at the idea of you want at most people surveyed, so we go back to the idea that we're taking 6 randomly selected people out of our classroom, and I want at most 2 people surveyed to believe that UFOs exist. Well, at most 2, that means I want the probability, is it going to be greater than or equal to 2, less than, or less than or equal to 2? I want the probability of less than or equal to 2 of success stuff. So that means it can be, I can have 0, I can have 1, or I can have 2 people. So I'd have to do this 3 times and add it together. Same thing we just did in the calculator. I would have done that Bino PDF with that K value of 0, K value of 1, and a K value of 2, and just added them all together. Or, since I'm combining up to 3 values, I can use the CDF value. Okay? I can do the CDF. So the probability of getting at most 2 successes out of our selection of 6, that means I have 0, 1, 2, 3, 4, 5. There's our 6. The most 2 would have been these values. So if I put that into my calculator, it's I want to make sure I give you the way. In our CDF version, it's our Bino CDF. Again, number of trials, our P value, and now it's our up to K. This value is going to take the last comma stuff, is going to sum it from the beginning, 0, up to whatever you tell it. So it's going to add up the values from 0, 1, and 2. These are great for when it's at most style problems, up to 2 successes. If it's going to be an at least, bless you, you're going to use the complement. And I'll show you how that works. It would have been, if I wanted at least 2, that meant I could have 2, 3, 4, 5, and 6. So I would have taken 1 minus up to 6 and done it that way. It would have backed out the other ones. It's pretty cool how it works. Yes, ma'am?
So you actually type in up to,
We want, because we're looking at most, so we're going to get up to 2, it's going to add up 0, 1, and 2 for us.
but like you don't need to take the.
No. This is just the value. So it'll be up to 2. So we're going to put a 2 in here.
So you just put
Yeah, that's what it's calculating. So in mine, again, it's second vars up to B. Number of trials, again, it's 6. Our p-value was, I'm going to go right off the book one so I can show you how it matches the book stuff here. I'm using 0.37 this time. Our x value is going to be 2, because that's what we're going up to. And it should add up all 3 of them.
Sweet.
So if you go back and look at what we had here, the probability of getting all 3 of them would have been, well, the probability of getting 2, 1, or none. And you're adding up those 3 separate values, and you're getting it. It's just doing it for you. Okay, it's doing it for you.
That is
What's that? What's one thing I want you guys to start to see is that look at these histograms, these bar charts. See how they're belling out?
I come to a
Yeah, they're no peeking. So what's happening is that sorry, yeah, that was really bad. What's happening is that as we use larger and larger values in a binomial experiment, it's going to normalize itself. And that's where this normal distribution, the bell curve, comes into play. Remember that?
no.
You ever seen a bell curve? Standard deviations and things like that. Mean in the middle, standard within standard deviations. You've seen that on like standardized tests where they say you're within 1 standard deviation or so within the mean and all that.
Sure.
This is where all this stuff comes into. Let me show you another example of where you're using at most. Let's look at these 2 real quick. If I'm looking at these 2, I'm not going to use the formula. I'm going to use my PDF or my CDF. Calculate the probability of k successes for a binomial experiment consisting of n trials with probability p of success on each trial. A k value of 7, an n value of 12, and a p value of 0.7. Is that going to be a PDF or a CDF problem? PDF. It's a PDF. It's a PDF problem because it just equals 1 specific value. So in my calculator, it's going to be the binom PDF. What goes first? N, which is 12, comma, 0.7, comma, 7. Gives you my answer. Whereas the other one, it says less than or equal to 3. It's a CDF problem. Now, what I want you to think of is you have n number of trials of 14. So we start at 0. I want the number of successes to be less than or equal to 3. Yes, sir?
So PDF is when K is an exact number,
Yep.
CDF is when it's a rounded number.
In this case, I have I want to be less than or equal to 3. So that's just going to be these numbers. What am I counting up to? 3. So in my CDF, it's still number of trials, p-value 0.45. In this case, it'd be 3. Oh, thank you. I looked at, where did I get 12 from?
The last one.
Probably. All right.
So why would it go up to-
What's that?
Isn't that asking for greater than
Oh, no, it's saying you want the number of successes to be less than or equal to 3. Now, when you want number of successes that are greater than or equal to 3, that means you're going the other direction. You're going this way. You want all of those. If the k value was greater or equal to 3. Now, here's how you would do a greater than or equal to. A greater than or equal to is still going to be used as CDF, but you're going to use the complement. What you would do for this one, for a greater than or equal to 3 with the same n trials p-value, it's going to be 1 minus the CDF of, well, we still do the same idea, number of trials, 14, p-value of 0.45, but what's it going to add up to? It's going to add up to 2. You're going to find the probabilities of these, take the complement, and it gives you all of that. That's how you work with going greater than. You pick the number preceding it, and you use the complement. It's a lot easier than trying to do, we used to do this with tables and all this other stuff and do this all longhand. It's much, much easier now. I'm only going to give you a couple of these to start with. We'll worry about the actual word problem stuff tomorrow. What I want you guys to do is, this is 12-6, it's page 742. Let's do 10 through 34 evens. Okay? And we'll build out of this more tomorrow and talk about how you can set up some of the word problems that work with like batting averages and things like that. Because a batting average problem, number of successes, you get 3 hits out of 4 using your batting average. You have success versus failure. It works the same way.
No, we don't have that much time. Thank you though.
You play
Do 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 do.